Nobody really knows what dark matter is. It has never been detected. That's why we are trying to see it using data. I'm a statistician, so my job is to use numbers, formulas, or plots to detect what otherwise would be unobservable. Indeed, the beauty of statistics is that it can be applied to any science. It's also translational. If designed correctly, the same statistical tool can solve many different scientific problems. I was doing a master in statistics at Texas A&M, and I attended a talk, and this talk was in the field of astrostatistics, which I didn't even know it existed before. And I always had some interest in physics anyway. And already when I was in Italy, I looked for application in physics, but nobody really knew anything about it. Nobody could help me to address this interest. And when I got to know that this field existed, so it's essentially statistics applied to physics or astronomy, I looked around for graduate programs in the area, and I managed to get a fellowship, PhD fellowship at Imperial College in London. And the title of this fellowship was Statistical Issues in the Search for Dark Matter. So I had I didn't even know myself what dark matter was at that point, and I don't really have a formal background in physics. So my understanding of the area itself was very limited, but all I needed to know really were what we were trying to find, what were the statistical issues arising, like if you want to formulate this physics problem into a statistical problem, what do we have to do and what are the statistical tools that we need? And so my job was just to work on this statistical tool, develop some methodologies that can be of help in detecting dark matter. But I really didn't have to study in the details the physics, thankfully. Otherwise, I probably wouldn't got a PhD. But yeah, so. So my work is, first of all, my area itself, there are not many people who work in this area at the moment. And many people I know who work in this area mostly work with astronomers rather than particle physicists. It might be because my co-advisor was a particle physicist that I'm more interested in this area. I mean, in some sense, I was kind of raised academically in this area, and so I have a stronger interest for particle physics, which is slightly different from many people in the astrostatistics area. So now, what I'm trying to do is to develop methods that can address problems in this area, but at the same time maintain the universal character of statistics, really, meaning I'm motivated by problems in particle physics. I want to develop tools for signal detection of new particles, but then I want the same tool to be able to help, say, biologists to find genes that might be related to certain disease, or neuroscientists to find activity in the brain of people with certain problems, certain diseases again, or mental issues. So I really trying to make methods that are general, but then they may find immediate application in potentially groundbreaking scientific problems. I mean, if they really find dark matter, this is a huge deal. So far as nobody has found anything, the physics community believes that within the next few years, probably less than 10, they will be able to find it, which is reasonable because the experiments are becoming more and more powerful, and so it's really possible. But yeah, so far, nobody has ever detected, and I don't know if they've used my tools or not. I've developed them and I published them. Let's see. So. Well, I mean, my theory really depends on is highly conditional on the physics theory, and most importantly of what people in the physics group with whom I was collaborated think it is. So the most common hypothesis that is made out of WIMPs, which means weakly interactive massive particle. And so the idea of weakly interactive means they don't interact with light as normal particle, normal matter. They are massive in the sense that they have a lot of mass. And but the reason why, and this is part of why we call it dark matter, because again, these particles do not interact with light, so that's what makes them dark. But again, nobody has ever detected WIMPs, so that's is an open area of research still. There is kind of a process that I should explain to answer properly the question. So during my PhD, I was doing some research on inferential methods, meaning statistical method that can tell you, okay, this difference is significant. To say that we're significant, you must use a certain statistical tool and so forth. So that's what inference is, essentially. The problem is that many of these methods were relying on complex mathematical constructs. So as soon as I start talking about this construct to either a physics community or even just statistics community, to people who were not expert in that specific area of statistical theory, it felt like I was not creating any interest. Like people were not really interested simply because it was kind of complicated to even just understand the framework. And so who will ever even apply something like this? So from that, I've learned that if a solution can be as general as you want, as beautiful as you want, but if people cannot understand it, then we'll not use it. So the current area of research where I'm working on involves methods that are simple fundamentally, in the sense that the theory behind, if somebody studies it properly, is really simple, but at the same time is really powerful. So that's the statistical framework I'm using, and that's the statistical framework where I'm developing my tools. So essentially, I would like people to know that is really nothing difficult, even if the equation might sound scary sometimes. Is really the foundation is really simple, and that's what makes it beautiful. A formula is elegant if is first of all is as general nature. And so it does not rely on too many assumptions, and that's what makes it general. So if a formula needs many hypotheses to work, that's probably not as generalizable as we would like. And if you want, so the lower the assumption, the more general the potential application of that. So you already know by the list of assumptions, or not just the number, is really how strong the assumptions are. I mean, maybe I have, in general terms, suppose I design a dress. It's wonderful, but it only works on people with red hair. I mean, it will look wonderful, but only on people with red hair. So, I mean, it can be the best dress, but only redhead people will wear it, you know? So, similar. You want a formula which very few and weak assumption. And if you want to test it works, well, people generally use numerical simulation and numerical methods. And this is something that, thank God, we can do nowadays with the powerful computers. But yeah, otherwise, I mean, obviously there are proofs. So like the proof is the main thing. So. Well, basically by chance, as the discipline probably is representative of that. So And during my high school, we had, so in Italy, first of all, you have to select your major already when you're still in high school before even entering the university. And so I decided to go for statistics because during an orientation program, I got to know that statistics existed, first of all, because it's not really known as a discipline even in Italy. And so one man who actually works in the National Institute for Statistics in Italy was talking in my high school, and I got to know it exists. I got to know it's an applied, a field of applied math, and I liked math, but I wasn't really sure of what I really wanted to do. I mean, I know I like mathematics. I don't like the theory behind it. I like the applied side. I like physics because it's in some sense, can be seen as an application of math. It has some practical utility. And so I didn't know if I wanted to go in engineering. I was also good in art, so I was considering architecture as well. I was interested by the medical sciences, so I had no idea what to do. And statistics was the only one that somehow allowed me to keep all my doors open, in the sense that you can really apply statistics to any area. I knew that there are application in environmental sciences, in medical sciences. I didn't know at that time in the physical sciences as well, but in economics also. And so that's why I decided to go for statistics, basically to have the freedom of choosing the area of application later on and not at 17 years old, basically. Actually, there is a very interesting story about my interview in Minnesota, but I don't know if you want. It's funny, actually.
Yeah, tell me.
So basically, I applied to several places, many places actually, because I was graduating from London, Europe, and so I didn't know what were my chances. So I applied to several schools, different ranks, and so. And at some point, University of Minnesota School of Statistics contacted me, which already came as a shock because I did not expect I could be shortlisted by such a high-ranked Department of Statistics. And well, then I got shortlisted by others equally or higher in ranking, but ranking is just like, irrelevant in general. But anyhow, so I got shortlisted, and okay, we scheduled the interview, and I still remember I was supposed to deliver my talk on January 23, 2018, and I was flying from Boston to Minneapolis, and my plane stayed on top of Minneapolis airport for about 1 hour and 30 minutes, and then they decided to close the airport and send us back to Chicago, and this was 6:30 of January 22nd, means, in 14 hours I have to start my interview at the University of Minnesota, and I'm in Chicago. So then they sent me in a hotel, and they said the flight is gonna leave at 6:30 in the morning. Okay, obviously I emailed the head of the department and everybody. I went to the hotel. All the passengers diverted from Minnesota to Chicago were in that hotel, so 2 hours check-in, and these people decided to make the most out of it, and they basically drank at that party all night because I couldn't sleep. I mean, I didn't sleep a single hour. So I went to the airport, and the flight was again delayed and it would leave at 9. So my interview was starting at 8:30. I was like, it's just not possible. And so I arrived at the graduate hotel. So I arrived on campus, and Galen, the head of the department, walked me to the place where I was supposed to deliver the talk that was rescheduled for noon. And so I reached that room after all this at 11:57. And somehow I managed to deliver a good talk. People were laughing at me because I generally put jokes in my talk and stuff. So I was very relieved, but it was really a surreal experience almost to even just get there. then I don't know if it was, they knew what I went through. So I don't know if they were particularly, I didn't even think about that. I don't think they were particularly accommodating because the people I met at the interview are still the same people I'm working every day. And it's not that they were faking or anything, No, it's really a wonderful department. I've interviewed in many, many places. And regardless of, say, the ranking or the labels, because when you are a graduate student and you're looking for jobs, that may matter. But then you have to think about what is the place where I can see my idea to flourish at some point, where I have all the conditions that I want to make sure that will happen. And when I came here, I met very nice people that were really supportive, that they were not, they were asking me many questions to learn from my work, not to challenge me, say. And I learned a lot already during the interview from the other professor. So I really I remember I taught this department as the department where if I may not get an offer from anybody, but if I don't get an offer from Minnesota, I would humanly feel bad. It's it's kind of personal, So I thank God I did. They made an offer, so I came here. It's working out, so I'm happy. I'm teaching 2 courses. One is for a senior undergraduate in statistics. So that last year went fantastic because was 17 students, which means we can interact more in the class. And when it ended, I really felt I'm gonna miss them. It's like I have 17 little cousins. But this year I have more students, so it's a bit harder to make everybody interactive, but it's still going well. And this is fairly easy class in the sense that everybody starts from the same level, everybody has the same background, and they like the teaching style, the notes and stuff that's partially come from England, partially come from Texas. So it's a mixture of everything that worked for me. But then the second course is a bit more complex because last year I was teaching to senior undergraduate in sociology, senior undergraduate in statistics, PhD student in math, PhD student in environmental scientist, master in data science. It was like a really broad audience that it was challenging, very challenging at the beginning to make them at the same level and make sure everybody started at the same point in some respect. And so that was very challenging at the beginning, but then it worked out well. So I kind of had to adjust myself more in that course, but I guess it worked out. They seemed happy. Basically, I started I got officially my degree from Imperial College on August 1st, and on August 13th, I started as assistant professor. And 1 month later, so it's around September 3rd in 2018, I started teaching. And it was, the transition was really hard. But that's just because I remember myself, and it was like up to a few months earlier, a very demanding student. Really, I always expected a certain standard in teaching, and I wanted to deliver that standard to my students. So it took me a long time to design the courses I was teaching. It took a lot of effort, but and I did try to merge several teaching styles. It has to be something that involves them. It has to be active learning. That's how they call it. I didn't know it has a name before, but that's how they call it. And so that they get involved during class. They don't get bored. It's not just me saying things that they will never understand unless they read them carefully. So they can stay attentive. And so it's working out, both in class and they can see the result. Every course ends with final report, exam that they do, basically an analysis, a statistical analysis they do alone at home. And you have to show what you have learned in a semester. And when I read the report, I'm always very often impressed, honestly, because they really, that shows how much they have learned. And yes, I mean, that's rewarding already for me. I mean, I can see my students are capable of something. I can see their reasoning process, and so that's really important. I want them to develop a way of thinking such that in statistical terms, such that they will not be replaceable by robots in 20 years. Because when it comes to computational sciences, well, statistics is not really a computational scientist, but it has its computational sides. And if somebody wants to be strictly apply statistical tool without really understanding them, it's possible. So I want them to understand what they are doing and why they are doing and why what they're doing works, rather than just, okay, I've applied it, this is what I've got, I'm happy with it. And simply because, I mean, they have to make a reasoning that I didn't have to make when I was at their age or at their stage, which is I have to be able to develop some skills that will not be replaced by the automatization by artificial intelligence or whatever. And so they have to learn to think, and they have to learn to hopefully be innovators in some sense. But this is a much bigger challenge. So.